what's nucleosome? So you know that your DNA in each cell will be 2 meters long, but we have to package in micrometer size of the nucleus. So the way that nucleosome can be packaged from a linear form to a compact form is by having DNA wrapping around this container to become a nucleosome. So nucleosome is a basic unit for DNA packaging. And both our lab and TJ's lab, we are working on the interaction of protein on DNA. So that's why we need to care about nucleosome if you're needing to work on any system that exists in mammalian cell. Okay, so that's why it's important to know about nucleosome. So what we need to know? We need to know about nucleosome position, nucleosome structure, and nucleosome dynamics. It's known that DNA sequence has an effect on nucleosome position. It's being published by maybe Wyden's lab and many other labs. But it's not too much known about how DNA sequence can affect on nucleosome structure or nucleosome dynamics. That's why I'm interested in studying the correlation of DNA sequence to nucleosome structure and nucleosome dynamics. So how I did it? We are in TJ's lab, so one of the powerful tools is using FRET. Yeah. So for using FRET, we have a FRET dye label on DNA. So I didn't mention that the structure of nucleosome at this, and now I should tell you. So nucleosome has about 147 base pair of DNA wrapped around this one octamer by almost 2 tons. That's why we can have a trick of having a FRET dye on 2 tons of DNA for studying the dynamic or structure of the nucleosome. So another tool that I use to study the nucleosome dynamics is using the combination of optical trap and then fluorescence. So why do we need to use this setup? Because we want to study the dynamics of nucleosome under tension. Because in the cell, nucleosome is likely to be in contact with any other compartment or under the polymerase or enzyme acting on it. So it's likely to be under tension. That's why we want to know about nucleosome dynamics under tension. So the way I'm using this setup to study the nucleosome system is that I have a tether of lambda DNA connected to one end of DNA on nucleosome. So this tether will be connected to a bead. So now you have this system. The bead will be a trap by an optical trap. The other end of DNA is immobilized on the surface. So now if we fix the trap and then we move the stage. So that's why we can do the pooling on nucleosome. And we have a thread on DNA, so we can use green excitation to look at how conformational change of the nucleosome will happen under the force. Okay, so now how do I correlate nucleosome structure and nucleosome dynamics to DNA sequence? So fortunately, we have a fusion to do the DNA cyclization assay to study the flexibility of DNA sequence. The idea is that if you have a short fragment of a double-stranded DNA immobilized on the surface, you put 2 sticky ends, which has side 3 and side 5. So if you have it in a linear form, then you have a low threat. But there is a chance for the loop to form, then you have a 2 die close to each other. That's why you can have a high threat. So by looking at how fast this loop being formed, then you can correlate it to how flexibility of the DNA is. Okay. Sorry, and here's the result. What we saw with the force is we saw that nucleosome being unwrapped asymmetrically. So one half of the DNA being unwrapped easier than the other half. Why is that? It's because of the one half of the DNA is more flexible and the other half is stiffer. And if we change the flexibility of DNA, we can flip from the weak side to the strong side and strong to the weak. Okay, so now forget about the graph. All you need to remember is the flexible side of the DNA by nucleosome stronger. Okay, and how about the structure? A zero force. What we saw is nucleosome can undergo Spartan switching. Sorry, I'm done with 5 minutes. Okay. Can I buy 1 more minute?
Buy 1 more minute.
combined with other control experiments, we think nucleosome undergo a gap transition. So you have the two turn is parallel if you have a higher fret, and in a rectangular angle if you have a lower fret. And we saw that on the flexible side, when we bring the source, nucleosome is stable at a lower fret stage. That means it's stable at this conformation on the flexible side. But on the stiff side, you saw that it goes to a higher fret, which increasing the more source. So that means nucleosome is stabilized at a parallel configuration at a higher source on the stiff side. So what does this mean? Okay, now forget about this graph. All you need to remember is the flexible side stabilize the gap configuration, and how this gap configuration helps. It has been shown that if you have a gap, that means you are in a rectangular shape, so it's easier for nucleosome to be compact in chromatins. So that's why more flexible DNA help to compact chromatins. Okay. So using the combination of three techniques in our lab, what we learned is flexibility of DNA will affect nucleosome dynamics and nucleosome structure. Okay, let's remember again, flexible meaning stronger, and flexible compact chromatins. So for future, what we want to study is, from fusion study, we know that if we modify DNA, for example, we can introduce a mismatch, then we change the DNA's flexibility. So in the future, what I want to study is to study the correlation of how the modification of the DNA can affect nucleosome dynamics and chromatin structure. And another thing that we know is nucleosome dynamics and nucleosome structure will definitely affect any DNA-involved process, for example, transcription, replication, or repair. So what I want to move on is to study how the modification on DNA will affect this process. Okay? I hope that is clear.